So we've talked about subspaces, we've talked about spanning sets and the span of a set, and how there's a link between subspaces and spanning sets, and the span of these spanning sets. Let's see if we can take a better look, or a more in-depth look, at the subspaces of Rn. Right? Rn is our prototypical vector space. If we understand things that are happening in Rn, then there's a good chance that we'll be better able to understand things in a general context, right? It's not enough to know what's happening in Rn, but because most vector spaces behave like Rn with respect to vector addition and scalar multiplication, then this is a good place to start. So we'll take a look at the subspaces of Rn for 1, 2, 3, and that's going to give us an idea as to what happens in the general case, a general n. The subspaces of R, well, there's only two. Well, we know that the zero subspace, which is to say the set that only contains the zero vector, and I need to remind you, this is not the same thing as the empty set. The empty set would have nothing in it. The zero subspace has 0 as a vector in it. That's a subspace of Rn. We know that for any n. So in particular, the zero subspace, which is to say the set that only contains the zero vector of R, and the zero vector of R is just 0, the scalar, that's a subspace of R. Now, if you have any other subspace W which isn't just the zero subspace, so it contains something, call it X, which is not 0. If not, then the only thing it contains is 0, and then we're back in the zero subspace case. So if I have a subspace which is not the zero subspace, it has to contain something which is not 0 in it. In particular, it contains every scalar multiple of that X. Now, X here is written as though it was a vector, and it is, but it is also an actual number X, because the vectors in R are just scalars. They're just tuples with only one component. So because W is a subspace, it is closed under scalar multiplication, which means that R times X is in W for every single R in R. So R times X is in W for everything. And because X is not 0 and R can be taken to be any real number, what we have here is this can take on any real value as well, right? Or in other words, if you pick any Y in R, you can write it as Y equals Rx. It's not difficult. The X, we know that it exists because W is not the zero space. All you need to find is the scalar that will do the trick. We'll pick R to be Y divided by X. I know that this exists because I'm not dividing by 0. So this exists. And I can write Y as R times X. So any real number can be written as R times X. So it is in the subspace. And so the subspace W then has to be the entirety of R. There are only two subspaces for R. There's the zero subspace, and then there's R in itself, in its entirety. For R squared, for sure we will have that the zero subspace, which in this case, the zero vector is a vector with two components because I live in R2. For sure the zero subspace is a subspace of R squared. And for sure R squared is a subspace of R squared because R squared is contained in R squared. It's exactly the same. And we know that R squared is a vector space. So R squared is also a subspace. Great. So we at least have two subspaces. It turns out that there's only one other type of subspace in R squared, would be lines through the origin. How are we going to show this? It's either the zero subspace, all of R squared, or a line through the origin. Well, let's pick W, an arbitrary subspace of R squared. I don't know anything about W other than the fact that it's a subspace. If it turns out that this W is in fact a zero subspace, we're done. It is one of these three things. We're happy. If W is the whole of R squared, we're also happy because, it's one of these things. Now, let's say that W is not the zero vector subspace. Then there's going to be at least one vector in W which is different from zero. And because W is a subspace of R squared, then we know that W must contain the span of V, because V is already in W. That's from the big theorem on spans. Span of V, that's a line through the origin with direction vector V. So if W is in fact the span of V, as opposed to just something that is contained in W, the span of V, then you're done. You have that the subspace W was a line through the origin. So let's say that W is not the zero subspace and it is not the span of V, and we knew that V was a vector in W that wasn't zero. Then W must be bigger than the span of V. So it's got to contain something, let's call it W, which is not zero and which is not on the line spanned by the direction vector V. Otherwise, well, W would be the span of V. So V and W are not collinear. I'm calling it collinear now. You might remember this expression from high school. What we mean is that they are not parallel to one another. So we have V and W that are in the W, the big subspace W. From the big theorem on spans, what this tells us is that the span of V and W must be contained in W. So this has to be in W. We'll be done if we can show that in that case, that span of V and W is in fact R squared. If it is R squared, then we've, hit the third possibility. So it's either the zero subspace or a line through the origin or the entirety of R squared. So how do we show that the span of these two vectors VW, which are not parallel, is in fact R squared? What we need to do is to show that any vector in R squared is also in this thing. And we'll be done. Why? Well, we've already shown that any vector in the span of VW is inside of R squared. How have we shown this? We've shown it because V and W are themselves vectors in R squared. And if you take any linear combination of vectors in R squared, which is what this span here would be, you have to still be a vector in R squared. So we know that the span of VW is a subset of R squared. If we can also show that R squared is a subset of span of VW, then we don't have a choice. They have to be equal. The only way for A to be a subset of B and B to be a subset of A is if they're in fact the same set. So what we need to do then, to complete the theorem, is to show that any vector in R squared, let's call it arbitrarily U, can be written as a linear combination of V and W. All right, so we're going to write that out explicitly. V is going to be the vector V1, V2. I write it here as a row, but it could also be written as a column. W is the vector W1, W2, and U is going to be the vector XY. That's the arbitrary one. What we need to show is that we can always find a solution in the unknowns A and B. So we can always find a coefficient A and a coefficient B so that U is equal to A times V plus B times W. So can we always find the solution in the unknowns A, B? Can we always find the coefficients A, B? If we can, we should be able to solve the following system. X, which is the first coordinate of U, should be equal to A times V1 plus B times W1. And Y, the second coordinate, should be equal to A times V2 plus B times W2. Now, it looks as though we just have a bunch of unknowns here, but we don't actually have that many unknowns. The only things that are unknown are A and B, or at least variables. X and Y, we don't actually specify what it is, but it's a point that we've selected. So in theory, we know what X and Y are. The same thing goes for V and W. They were vectors that we found in W whose existence we knew. Now, we don't know what they truly are, but we know that they exist. And we know that they're fixed. So when I say that they're not unknown, what I mean is that they're not variables. They're not things that we have to find the values of. The only things we need to find the value of is A and B. So how would we verify this? How would we do this? Well, you can show, and later on we'll see how to solve this system of equations in A and B. But you could verify that this expression here actually does give us a linear combination of V and W, which adds up to the vector U. How would we do this? You'd replace V by V1, V2, and W by W1, W2, and U by XY, and you'd actually spell it out fully, and you would get that this whole thing is A, this whole thing is B, and you get an equality. So you can always find A and B as coefficients, such that you can write any vector in R squared as a linear combination of V and W. This only makes sense as a solution, though, if this coefficient A and B is defined, meaning that you're not dividing by 0. And this is the same denominator in both cases. I'm going to tantalizingly get you to notice something. V1 W2 minus V2 W1. So that's V1 W2 minus V2 W1. Sort of a weird cross product. It's not the cross product that is truly the cross product of two vectors in R3, but it certainly looks like the cross product that was like each of the components of the cross product in R3. So there's something there that's sort of interesting. It's linked to the determinant of matrices, which we'll talk about shortly. So we also have to make sure, before we say we're done here, that this thing here cannot be equal to 0. Otherwise, we're dividing by 0, and our solution, our proof, is not a true proof. So how can we show that this expression cannot be equal to 0? Well, we have possibilities, right? If V1 is equal to 0, if the first coordinate of the V vector was 0, then the second coordinate could not be equal to 0. Because if it was equal to 0, then we'd have both V1 and V2 being equal to 0, meaning that V is the 0 vector, but by assumption, this vector V that we found was a vector which was different from 0. So it's impossible to have both V1 and V2 being equal to 0. And say that one of these has to be different, at least from 0. In that case, when you look at the expression V1W2 minus V2W1, well, that first term would be 0, so that would disappear, right? Because we're assuming here that V1 is 0, and you're just left with this one, so minus V2W1. Now, the only way for this to be 0 would be for W1 to be 0, because we've excluded the possibility that V2 would be equal to 0. Otherwise, the whole vector V would be 0. All right, so if W1 is 0, well, you can't have simultaneously that W2 is 0. So if V1 is 0, the only way for this expression to be 0 is if W1 is 0. And then that would be a problem because you'd have V, which would look like 0 V2, and W, which would look like 0 W2. They would both not be equal to 0, but they would be multiples of one another. One is a scaling of the other, which means that they are parallel. And that's a contradiction, because we've assumed to start with that V and W were not parallel, that they were not collinear. So if V1 is equal to 0, you cannot have that V1 W2 minus V2 W1 is equal to 0. That's impossible. And if you had V2 equal to 0, you get exactly the same proof. You just switch the 1 and the 2 throughout. Okay, so if one of these is 0, one of these coordinates, it's impossible for you to have that the full expression is 0. Okay, what if they're not 0? What if they're both different from 0? Well, if V1 and V2 are both different than 0, for sure, then the vector V is different from 0. That's good. But the only way for V1W2 minus V2W1 to be equal to 0 is if you had, send it over to this side, V1W2 equal to V2W1, or in other words, if I divide both sides here, 1 by V1 and 1 by V2, that W1V1 is equal to W2V2. Now, if both of these quantities are exactly the same, we can call them K, give them a name. And this is a fixed quantity, right? Because V is known, W is known, V1, V2, W1, W2, they're known, they're fixed quantities. Even though we don't actually know what the values they take, they are known. In that case, you would write W1 as K times V1 by literally multiplying both sides by V1, W2 by K times V2. In other words, W as a vector would be equal to K times V. And that's also a problem because we've assumed that W and V were not collinear, that they were on different lines through the origin. So it is impossible then to have V1 and V2 be different than 0 and this expression be equal to 0. No matter what happens to V1 and V2, the expression V1W2 minus V2W1 cannot be equal to 0, and hence it makes sense to divide here by the expression. Okay, then we've shown that if W is not, if W is a subspace of R squared, then either it is the 0 subspace or it is the span of a non-zero vector, so a line through the origin, or that it is the entirety of R squared. These are the only options. So for R, the only options are the 0 subspace and R in its entirety. For R squared, the only options are the 0 subspace, a line through the origin, there's infinitely many of them, and the full R squared. What about R cubed, R3? Now you know, as before, that the 0 subspace and R3 are subspaces of R3. And that's the same result as in R2 and R1. But there is a result that is quite like the result we saw for R2. The only subspaces of R3 would be the 0 subspace, lines through the origin, planes through the origin, and all of R3. These are the only possibilities. We'll do this proof later when we have more tools at our disposal, but I'm going to give you here a little geometric argument. Let's say that W is an arbitrary subspace. So it's some subspace of R cubed. If it's the 0 subspace, then you're done because it's one of the options. If it's not the 0 subspace, then you can find a vector V which is not 0, look at the span of that, and because V is in W, then the span of V will be in W by the big theorem on spans. If it is in fact equal to the span, if W is a line through the origin, then you're done because it's one of the two options. If it's not equal to the span of that one vector, then there's going to be some other vector W which is in the set W or subspace W, but which is not in the span of V. And so that means that the span of V and W will be contained in the subspace W. And in particular, that W that you pick is not parallel to V. Now, if W is this full span of two vectors, then that's a plane through the origin and you're done. If it is not the full span, then there's some other vector, call it U, which resides in W, but is not coplanar. Coplanar, I don't know how to pronounce this word, not in the same plane as V and W. And then afterwards you can show that you don't have a choice really. If that's the case, then W is the full of R cubed. Every vector in R cubed would lie in the span, and you're done. But that's roughly speaking the argument, and you see that it's basically the same argument. The hard part or the difficult part would be here to demonstrate that that's the case, that you can write any x as a linear combination of these vectors. It's not obvious. It's doable, though. It is left as an exercise for the students. I'm going to use a bit of time here to mention something which is going to play a role. You might have thought that my choice of words was, well, because I'm not a native English speaker and I'm not using the right words when I talk about these things. No, I rather specifically use the indefinite article a when talking about spans. We don't talk about the span, we talk about a span. The thing is, I guess I could talk about the span, but there might be different spanning sets. There's a bit of confusion here, potentially, in the choice of language terminology that you use. It is conceivable that two different spanning sets give you the same span. That if you look at the same combinations, linear combinations of these two vectors, you will get exactly the same final set as if you were looking at all the linear combinations of these two vectors, even though the spanning sets themselves, just the vectors that are fundamentally in this set, are different. How would we know this? Well, I can write every vector in this second spanning set as a linear combination of these two vectors in the first spanning set. For instance, the vector 1, 1, 2 can be written as once 0, 1, 1 plus once 1, 0, 1. So the first vector in the second spanning set is a linear combination of the vectors in the first spanning set. And similarly for the second vector, minus 1, 1, 0 is a linear combination of 0, 1, 1 and 1, 0, 1. The linear combination is 1 times 0, 1, 1 plus minus 1 times 1, 0, 1. And so what that tells us is that the two vectors here, 1, 1, 2 and minus 1, 1, 0, they are in the span of these two vectors. These two vectors are linear combination of these two vectors. And because this is really the set of all linear combinations of the vectors 0, 1, 1 and 1, 0, 1, then these two vectors, on the strength of these linear combinations, belong to the span, that first span. So by the theorem on spans, what this is telling us then is that the span of these two vectors also has to be contained in the span of the first spanning set. Well, we can work it out the other way as well. We can write each of the vectors in the first spanning set as a linear combination of the vectors in the second spanning set. I'm telling you what these linear combinations are. 1/2 of the first plus 1/2 of the second, and then 1/2 of the first minus 1/2 of the second. And so what that tells us is that the two vectors in the first spanning set are in the span of the second spanning set. And again, by the big theorem on spans, that means that the span of these two vectors, the span of the first spanning set, is contained in the span of the second spanning set. And we're in this situation where W is in U is in W, contained in U is contained in W, and so W and U have to be the same spaces. Sometimes, though, the span of two vectors will not be equal to the span of two other vectors. You can't really tell just by looking at things. It's not always obvious. I mean, sometimes it is obvious, but some of the times it is not. So there's a bit of a ambiguity there. The spanning sets for a given span are not unique. And sometimes they don't even have the same number of vectors in the spanning set, and they still give the same spans. The span of 0, 1, 1 and 1, 0, 1 is a subspace of R3 that we know. The span of 0, 1, 1, 1, 0, 1, 1, 1, 2, and minus 1, 0 is also a subspace of R3 because it's a span of vectors in R3. So that these are both subspaces. But that they're equal is not immediate. I mean, it shouldn't be too complicated. We do see that these two here have exactly, or have a twin here. But how do we know that adding these two other numbers, 1, 1, 2, and vectors, 1, 1, 2, and minus 1, 1, 0, doesn't somehow change the span? Well, it's easy to see that on the left, the two vectors in the spanning set have to be in the span of the four vectors because they're directly in the spanning set. And there's a linear combination. It's just put 1 in front of the vector and 0 in front of everything else. And so you'll find that. So you can show easily that the span of the first spanning set is in the span of the second. We also happen to show that every one of the vectors in the second spanning set, there are 4 of them, are in the span of 0, 1, 1, and 1, 0, 1. We happened to do this exercise previously. So we were able to write every one of these 4 vectors as linear combinations of the only 2 vectors in the first spanning set. And that tells us that both spanning sets are inside of one another, are contained in one another, and so they must be equal. So the number of vectors in the spanning set does not necessarily tell you something about the size of the subspace that is spanned by the vectors. Now, some of that might be confusing. You absolutely must understand the distinction between a spanning set and a span. Spanning set is a finite number of vectors that are used to build the linear combinations that go in the span. These two things are different objects. In French, we don't have this problem, right? The spanning set c'est un ensemble de vecteurs, and the span is called l'enveloppe vectorielle. So there's a difference between the way we refer to those. In English, unfortunately, span and spanning set sound like they should mean the same thing. They do not. The span is a subspace. It contains infinitely many vectors, unless it's the span of the 0 vector. And a spanning set, theory, can contain a finite number of vectors only. Okay? And you need to understand what the big theorem on spans say. The big theorem on spans say that if you have a vector in a subspace, then the span of that vector is contained in the subspace. If you have 2 vectors in the subspace, the span of these 2 vectors is contained in that subspace. You cannot leave a subspace by taking linear combinations of what's in the actual spanning set. That's the important distinction. We'll talk further about how we can differentiate spanning sets that are superfluous in a sense, that contain vectors that do not need to be there. Right? In this example, we have both of these being exactly the same subspace. In one instance, I only need 2 vectors to actually build all the linear combinations. In the other instance, I use 4. It turns out that I don't actually need 4, because if I needed 4, they could not possibly be equal. So how do we know how many we need. That's going to be the next topic.